Hi, this is the Semaphores chapter of our synchronization discussion. I would say the use of semaphores looks easy, but to use it effectively and correctly sometimes can be challenging. I used to say that there are two difficult components in this course. The first one is proving mutual exclusion of a solution to the critical section problem. The second one is semaphores. So this chapter or this unit will be divided into several short lectures so that you will be able to review each recording rather easily. So the definition of a semaphore is rather simple. A semaphore is just an object. This object does not have any public components. It consists of at least two private items. The first one is a counter. The second one is a waiting set. Now, if you have to say, regarding the public section, there are two public methods. Actually, they are member functions. The function signal and the function wait. So this is a semaphore. It is a private counter and a waiting list. So all threads that have to be waiting or blocked by this semaphore will be waiting here in the waiting set. The reason for using the word set is there's no ordering. Suppose here we have 4 threads, each of which is represented by a square. These 4 threads wait there. And sometime later, one thread will be released from this waiting set. But we don't know which one will be released first, because the word set means this set of threads is not ordered in whatever way. Although when we implement a semaphore, we could use an ordering. For example, first in, first out, or whatever way. So you cannot access the private counter. You cannot access this waiting set either. You don't even have the capability to know how many threads are waiting in this waiting set. What you can do with respect to this semaphore is through 2 methods, signal and wait. So although it is not very appropriate, you could consider semaphore is a traffic signal. If it is red, you wait. And when the traffic signal changes to green, you can go. So someone, if you are blocked by a traffic signal, someone must switch or flip the red line to green line so that you could go. When you can go, it means someone here, you are here, one of these 4 will be chosen. So again, what kind of order for releasing a thread from the waiting set is unknown. We will return to this point later. So the definition of the semaphore method wait is rather simple. So wait, in general, does not return anything. it takes a semaphore as its argument. Now, if you write a semaphore as a class, so it's going to be s dot wait. So the first thing in the wait method is subtract 1 from the counter. And then we test the new value of the counter. If the new value of the counter is less than 0, then the caller who calls this wait method will be put into the waiting set and block it. So in other words, when a caller calls a wait, after subtracting 1 from the counter, and if the new value is less than 0, the caller will be blocked and put into the waiting list. On the other hand, if the caller finds out after subtracting 1 from the count, and if the new count value is not less than 0, the caller will return. So a caller to the wait method could be blocked. If it is blocked, it would be in the waiting set. And of course, the other way around would be a caller will not be blocked. We'll see an example later on. So always remember this. When a caller or a thread calls the wait function, the first thing to do is subtracting 1 from the counter. If the new value is less than 0, the caller will be blocked and put into the waiting set. Otherwise, the caller returns. So in the second case, the caller is not blocked. It simply continues. And if the caller is blocked, it would be in the waiting set until it is released due to a signal call by some other thread. So the definition of the signal method is similar. First of all, when a caller or a thread calls signal, 1 is added to the counter. Now, if the new counter is less than or equal to 0, then we remove a thread from the waiting list, resume its execution. So when that thread is resumed, it's essentially equivalent to returns from his wait call. Now, the differences between signal and wait is wait, we subtract 1 from the counter. In signal, we add 1 to the counter. In the if statement, for the wait, we test for less than 0. For signal, we test for less than or equal to 0. For the wait method, if the condition in the if statement is satisfied, the caller to wait will be blocked and put into the waiting list, waiting set. On the other hand, for signal, the caller would remove a thread from the waiting set and resume its execution. In this case, both the caller and the resumed thread will continue. So for wait, the caller either is blocked or continues. For the signal method, the caller may release a thread from the waiting set. And in this case, the release the thread and the caller, which is also a thread, both continues. If the condition here is not satisfied, there will be no thread released from the waiting list, and only the caller continues, returns from the signal method. So let's take a look at a very simple example. I put the wait method here, and signal method here. So let's say we have 4 threads A, B, C, and D. We also have a semaphore S with initial value 2. Of course, if you have a semaphore in which you have a private counter, you have to initialize it to some way. Usually the initialization value is non-negative. Reason will be clear very soon. So what happened if threads A, B, C, D cause weight in this order? That's thread A cause weight, then thread B cause weight, then thread C cause weight, and finally D cause weight. What would happen? I will always keep this part here and using execution sequence step by step to illustrate what would happen. Now, this column shows thread A, thread B, this is what thread B does, and thread C, thread D, and the counter value and the semaphore waiting set. Now, because the initial value of the counter is 2, and initially the waiting set is empty. So this is the initial case. Now, let's go for the next step. Thread A calls wait. So that is thread A calls here. So thread A subtract 1 from the counter, making the counter from 2 to become 1. And because the new value 1 is not less than 0, therefore the then part of this statement is skipped. So the caller returns. So after thread A successfully calls wait and successfully returns from wait, thread A continues to run, and the semaphore counter becomes 1, and waiting set is still empty. Then thread B calls wait. When thread B calls wait, the value of the counter is 1. So B subtract 1 from it, making the counter value 0. But the new value 0 is definitely not less than 0. So the call will simply skip the then part and returns. Therefore, thread B continues its execution. And the semaphore counter is 0. The waiting set is still empty. So as we can see, every time a thread calls the wait, and if the current value of the counter is greater than 0, 1 is subtracted from the counter, and the calling thread simply continues. Now, we have new counter value 0, and we still have waiting set empty. So now the next one, thread C calls wait. Because the current value of the counter is 0. So after subtracting 1 from it, the new value of the counter becomes -1. Now, the counter value is less than 0, so thread C, the caller to wait, is blocked and put into the waiting list. Therefore, C is blocked. And the new counter value is -1. Now, C join the waiting set. C does not return. C is simply blocked here in the then part of this if statement. Now, what if we have D calls wait? In this case, when D calls wait, because the value of the counter is -1, so D subtract 1 from it, making it -2. -2, of course, is less than 0, so D is also blocked and put into the waiting list. Therefore, in this case, C and D are both blocked. They are put into the waiting set C and D. Now, from this very simple example, you know if the initial value is 2, we allow 2 processes to continue without blocking. And then when the counter reaches 0, every time a thread calls wait will be blocked. So as you can see, we block 2 threads here, C and D. The value of the counter is -2. When we block C, the value is -1. When we block D, we have 2 threads blocked. So the value of the counter is -2. Its absolute value is exactly the size of the waiting set. So far, it's very easy. I'm sure everybody knows this easily. Now, we know A continued, B continued, C and D are blocked in the waiting set. Now, what if A calls signal and B calls wait? In other words, after D is blocked, A calls signal and B calls wait. What would happen? As I'm sure every one of you should be able to figure out what would happen, but I need to point out one very important fact. It is here. Now, C and D were blocked in the waiting set, and the counter value is -2. Now, A calls signals. So A enters signal from here, adding 1 to count. So making -2 to -1. So the value of the new counter is less than or equal to 0. Therefore, we're going to remove a thread from the waiting set and resume its execution. So the trick is here. We have C and D in the waiting set. Which one is going to be released? Sorry, because the waiting set is not ordered. We don't know which one will be released. And this is what you have to understand in implementing your programming assignment. You cannot assume which one will be released when a signal calls, causing a thread to be released. So let's say D is lucky, D is released. So D, the execution returns from the wait call by D to thread D. So D continue, D release and continue. So A is never blocked because there's no way to block the caller here. So A continue to run. And then, as we mentioned on the previous slides, B calls wait. So when B calls wait, the value of count is -1. The semaphore waiting set is C. So after subtract 1 from counter, which has the current value, -1. So the new counter value is -2. Then this condition is satisfied. Therefore, the caller is added to the waiting list and blocked. So B is blocked and put into the waiting set. So at the end, we have B and C in the waiting set. Assuming that when A calls signal, D is lucky and released. Now, if C is lucky, D would be here and C continues. Then when B calls wait as, then the waiting set would have B and D. I hope if you did not follow this discussion thoroughly, I strongly encourage you to pause this video and review these 8 slides before continue. So if you reach here, I assume you have reviewed that 8 slides regarding a very simple example. Again, I have a wait here, signal here. As we've seen from the previous slides and explanations, if the counter value is less than 0, its absolute value counts how many threads are in the waiting set. Do you remember that? The reason is every time a thread is blocked, it is because the condition after subtracting 1 from the counter, the condition becomes negative. Every time you subtract 1, the counter goes down by 1. Therefore, its absolute value counts how many threads are in the waiting set. Unfortunately, most systems do not allow you to access how many threads are in the waiting set. So your program correctness cannot depend on the access of this counter value. Counter value does not belong to you. It belongs to the class, which is a private counter, even though you can modify the class by returning the value of a counter. But by the time you get a counter value, probably some other thread may have already called wait and signal, changing the counter value. So beware of this fact. The second one is, we also mentioned earlier, the waiting set can be implemented with the queue if first in, first out order is desired. However, the correctness of a program should not depend on a particular implementation, that is the ordering of the waiting set. You'd better assume that the order, if you really want to impose an order or assume an order, is going to be random. You won't be able to predict which, when you call signal and there are threads waiting in the waiting set, there's no way for you to predict which one will be released. So please remember this carefully. Now, the third one means the caller may be blocked in the call. Here, it may not be blocked. And after subtracting 1 from the counter, if the new value is less than 0, the caller will be blocked. The caller is never blocked in the call to signal. This is the signal. And adding 1 to the counter, testing the counter. And if this is satisfied, 1 thread is removed from the waiting set. And that thread returns from its wait call. But for the caller simply continues. So a caller to the wait call may or may not be blocked. A caller to the signal method may or may not release a thread from the waiting set, but the caller is never blocked. And the last one is probably the most important, and most of you will simply ignore it because it's just like an atomic instruction. The wait and signal method with respect to the same semaphore must be executed atomically, otherwise race condition may occur. What does that mean? Suppose I have a semaphore S1 and S2. Multiple threads could call wait and signal to S1, and multiple threads could call wait and signal to S2. Now, suppose we have thread A and thread B. They call wait at the same time. Because wait and signal must be executed in an atomic way. So when A and B call wait at the same time, only one will be successful. If B is successful, when B enters the wait method, A will be blocked outside of the wait method for S1 until B exit, then A could enter. The same reason applies to A and B call the signal with respect to semaphore S1 at the same time. Or even more importantly, if A calls wait and B calls signal with respect to semaphore S1, then only one can continue. Either A, who calls wait, or B, who calls signal, can continue. Which one, we don't know, just like the atomic instruction. However, if A calls the wait method of S1 and B calls the wait method of semaphore S2, because S1 and S2 are two different semaphores, we don't have this atomic requirement. Atomic requirement only applies to multiple calls to the same semaphore. Then the semaphore mechanism will serialize these calls so that these calls, concurrent calls, can only be executed one after the other. So let's say we have a homework. If wait and or signal is not executed atomically, please use execution sequences to show race condition could occur. Furthermore, if let's just pick wait as an example. If wait, the wait method is not atomic, then show that if you use the wait method to implement mutual exclusion, you're going to fail. In other words, if wait is not atomic, then mutual exclusion cannot be guaranteed. Well, we'll see the implementation of mutual exclusion later on. So now we know the concept of semaphores, but how do we use them? Actually, the use of semaphore is very easy. I said easy, but to use it efficiently and effectively, that is a different matter. So throughout my career in using threads and the synchronization, I can categorize the use of semaphore into three categories. The first one is to use it for achieving mutual exclusion. Usually, this is referred to as a mutex lock. Mutex is from mutual exclusion. This is the easiest one. Then we could use a semaphore to do a countdown lock. Remember, in our previous example, the initial value of semaphore S is 2. Then we allow 2 threads to pass through. The third one and the fourth one will be blocked. So the countdown lock is, simply put, it counts how many threads have passed that wait call. Once the counter reaches 0, all the subsequent threads will be blocked. In some way, the mutual exclusion is also a countdown lock because we just set the initial value to 1. Well, we'll see this later. But this one is more frequently used. And for beginners, usually you will scratch your head. scratch your hair because it's kind of not so easy to be used properly. In a threaded program, just like multi-process program, process must wait for something to happen before it can continue. So that process executes a wait, just like waiting for the completion of one of the child process. For thread, it's the same, just like the thread join. But process wait and thread join are very limited. We do not want to exit so that the creator could continue. In many cases, we need to communicate with each other. I ask you to do something before you can deliver the results. I have to wait until you get it done. Then, once I get your results, I continue. So this is referred to as notification. When I have to wait for your delivery of something. When you are done, you notify me, and then I continue. So this is notification. So let's take a look at an example, one for each of three categories. The first one is mutual exclusion, Mutex lock. Here, we define a semaphore S with initial value 1. I use a pseudo syntax rather than a actual syntax. So semaphore is a type of semaphores. S is the name of that semaphore. Equals 1 means I assign the initial value to it. And I have a count global value shared by thread 1 and thread 2 with initial value 0. Now, thread 1 add 1 to the counter. Thread 2 subtract 1 from the counter. So in this way, thread 1 and thread 2 access the global variable or shared variable count. They could access this count at the same time or in a concurrent way, as in the definition of race conditions. Without mutual exclusion, we have problem. And the results could be -1, 0, or +1. I'm sure you still remember this example. So how do we achieve mutual exclusion? We add s.wait as the entry code that followed by the critical section. The exit code is very simple. We just signal the same semaphore. So thread 1, thread 2 uses the same semaphore, S. So here, we will show you that we have, this is a very simple way to achieve mutual exclusion. But you have to ensure that the system you are using does support semaphore. For an example, C++ did not support semaphore until standard 11. So in this case, let's go through quickly. Suppose thread 1 and thread 2 execute s.wait at the same time. Remember, semaphore calls to the same semaphore. If they happen at the same time, then the semaphore mechanism would ensure the execution will be atomic. Only thread 1 or thread 2, even though they call wait at the same time, only one of them can go. So if thread 1 can go, so thread 1 would reduce the value of the semaphore counter from 1 to 0. And then because it's 0, not less than 0. So thread 1 returns and execute here. Now, right after thread 1 exit its wait call, the value of the semaphore counter has been changed from 1 to 0. So by the time thread 2 is allowed to call wait by the semaphore mechanism, thread 2 reduces the value of count to -1. Thread 2 waits. Upon exit, thread 1 calls signal. Currently, the semaphore counter is -1. So this signal would add 1 to the counter, making it 0. Now, the new counter value is less than or equal to 0. Therefore, thread 2 will be released, allowing it to execute the subtraction. But always keep this in mind. Thread 2 is released, and thread 1 could come back so fast. By the time thread 1 returns and calls wait, because the current value of the semaphore is 0. So subtract 1 from it, thread 1 blocks. Okay, so this is a very simple example. Furthermore, we could use as many threads as possible and only use one semaphore. So the use of semaphore, as long as it is supported by your system, is much easier than using the software solutions or hardware solutions. So let's take a look at an example. What if the initial value of the semaphore is 0? Think about it. Now, usually we will say if the counter value of that semaphore is either false or true, we will say the semaphore is a binary semaphore. For most systems, this kind of binary semaphore is actually called a lock or a mutex lock. Now, let's extend our previous discussion to give you a bit more. I copied the whole thing here, thread 1 and thread 2. A few things to remind you. The call to wait and signal with respect to the same semaphore has to be atomic. So when multiple calls to this wait and this wait, or even more to this wait, the semaphore mechanism will ensure that only one of the callers could get into the wait call. The remaining one will be blocked until the current one exits. Then the semaphore mechanism picks a second one. Therefore, even though we may have so many threads calling s.wait at the same time, only one can go. Which one? It's just like atomic execution of instructions. We don't know which one. So we can easily prove that this implementation satisfies mutual exclusion. Again, because no matter how many threads are there, if they call this s.wait at the same time, only one can go. The remaining one will be blocked outside of the wait. So we could assume that even though we have many threads calling s.wait, only one can proceed. That thread would reduce the counter of s to 0. And that thread exits or returns from the wait call because 0 is not less than 0. So meanwhile, when the successful thread is executing in its critical section, the remaining thread who called s.wait will be allowed to run. But again, because the call to s.wait is atomic, only one can go. When that lucky thread gets into s.wait, it finds out the current counter value is unfortunately 0. After subtracting 1 from it, it's -1. So that caller waits. Now, all the remaining thread, when they call s.wait at the same time, they would reduce the value of counter by subtracting 1 from it. They all enter the waiting set. And until thread 1, I assume that thread 1 is the first one to enter to the signal. That is the exit section. So no matter what, when this signal is called, it would release one thread blocked in the waiting set to continue. So as a result, if someone is lucky to get into the critical section, all the subsequent calls will be blocked. As a result, mutual exclusion holds. How about progress? Progress, let me remind you, involves two subcomponents. The first component is outsider influence. For this implementation, it's very easy. If a thread that is not interested in accessing the counter variable, then it's not execute wait, nor that execute any signal. It could have called a signal long time ago. So in that case, the value of the counter would not be affected by those outsiders. The second subcomponent of the progress is finite decision time. Finite decision time means when the critical section is empty and two or more threads are waiting to enter, then one of them will be chosen to enter the critical section in finite time. So a thread can be in its critical section, could be blocked in two ways. The first one is because the s.wait is atomic. And if we have multiple threads calling s.wait at the same time, that thread has to be blocked due to atomic requirement. But determining whether someone is lucky to be picked, that's definitely in finite time. So that one enters the wait call, subtract 1 from it, and does some testing. We only need finite number of instructions to finish subtraction and testing. Therefore, we have two possibilities for waiting. One, I could be blocked due to simultaneous calls to s.wait because of the atomic requirement. Of course, we have only finite number of threads. We take turns or in whatever ways, one will be allowed to execute the wait. Once that lucky one enters the wait, it takes a few instructions to finish the subtraction and the testing. And that one would go into the critical section. Therefore, for that lucky one, it takes finite time to get through. So the progress condition is satisfied. How about bounded waiting? I hope you can do it. A hint would be bounded waiting will fail. Bounded waiting means we have a bound. We have a bound, a known value. This known value is a function of the involved threads, number of threads. So if we implement this solution for n threads, so the bound has to be a function of n, just like the complexity for binary search is log n. the optimal sorting algorithm is n log n. So bounded waiting, we have to find the bound. So when I declare that I want to enter the critical section, I wait for no more than that number of bounds. So just use this two-thread pattern. Construct a execution sequence so that one of the two threads, say thread 1 or thread 2, could be starved. They don't have any chance to enter at all. Then we move on to the countdown counter. So here I have a semaphore S, initialized to 3. I only list thread 1 and thread 2. You could add thread 3, 4, 5 to thread n. Now recall that every thread that calls wait was reduce the value of the counter by 1. So if the initial value is 3, after 3 threads that will successfully pass s.wait, the counter value would become 0. The fourth one will be blocked. So say suppose in exhibit hall would only, which is very small, would only allow you to accept, say, 10 people. You cannot accept more than 10 people. Or in a restaurant, due to COVID-19, we have to give the safe distance from each other. So a restaurant may want to say, okay, I can only accept 10 customers. So we may have a person somewhere at the doorstep, and he or she may have a counter. When someone gets in, click. When someone click, every click reduces the maximum value 10 by 1, by 1, and by 1. When the counter reaches 0, the doorkeeper would simply say, stop, please, we are full. Please wait until someone exits. When someone exits, that someone would increase the counter by 1. So from now, then the next one could come in. So if you set the initial value of the semaphore to some value, say n or k, you allow k thread to pass through s.wait at the same time. Of course, if they call s.wait at the same time, they will be executed in a sequential way. But anyway, they could be in this section. I do not call it critical section because critical section will only allow 1 to be there. So this is the way for us to count how many threads can be allowed to perform certain tasks at the same time. Now, get back to the mutual exclusion. If I set the initial value of the semaphore to 1, every time you only allow 1 thread to be here. Isn't it the mutual exclusion requirement? Then let's talk about notification. When you use notification, sometimes you need to use your imagination and the creativity. Here I use a very, very simple example as a starter. In the next few lectures, we will talk about more examples. So I have 2 semaphores, S1 initialized to 1, S2 initialized to 0. Third one, initially wait on semaphore S1 and print 1. Then signal semaphore S2. And it loops back wait again. So thread 1 simply repeatedly execute wait for S1. When it can pass through, it prints 1 and then signals thread 2 and comes back wait for S1. For thread 2, it waits for S2. When it can get through, it prints out 2 and then signal. So thread 1, in usual language and daily language, thread 1 means I wait for the chance to print. After I finish printing it, I tell thread 2 who is waiting there in order to print 2. So this notification from thread 1 to thread 2 simply tells thread 2 that, oh, I have done my printing of 1. Please continue to print 2. Meanwhile, thread 1 may come back and wait on S1 again. Now, look at here. When thread 1 executes S1 dot wait successfully, the value of S1 has been reduced to 0. When thread 1 comes back and executes S1 dot wait again, the counter value of S1 is 0. So when thread 1 calls wait, the counter value is reduced to -1. So thread 1 waits. On the other hand, when thread 2 executes S2 dot wait, it reduces its initial value 0 to -1. So thread 2 is blocked until thread 1 signals it, because thread 1 increased value back to 0 from -1, and thread 2 is released. So thread 2 prints out 2. After that, thread 2 signal S1. Meanwhile, S1 may be waiting there. So in this case, thread 1 uses S2 signal to notify thread 2 that I'm done, please go ahead. By the same reason, after printing 2, thread 2 use S1 dot signal to tell thread 1 that I'm done, please go ahead. So it's like playing ping pong. 1, 2, 1, 2, 1, 2. So the printed out is 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. So I strongly encourage you to stop a while and understand what I have said before you can move on. So here is a execution sequence. Now here we assume if T2, that is thread 2, reaches S2 dot wait before T1 can execute S2. So that is thread 2 waits before thread 1 signals. So the initial values for S1 and S2 are 1 and 0 respectively. T1 execute S1 dot wait. And T2 execute T2 dot wait. So this S1 dot wait reduces the value of 1 to 0. This S2 dot wait reduces the value of S2 to -1. Therefore, thread 2 waits. Then thread 1, because the value is 0, it could go print the 1. Now this means thread 2 reaches S2 dot wait before thread 1 can signal. So in this case, thread 1 signals S2, returning the value of -1 of S2 to 0. And S2 is released. So meanwhile, thread 1 can come back, execute S1 dot wait, because now the value of 0 of the semaphore is 0. when this is executed, it becomes -1. Thread 1 is blocked. At the same time, thread 2 could print out 2. And then thread 2 signals S1, allowing thread 1 to continue, and so on. So that's one possibility. Now let's take a look at the other. That is, thread 2 reaches this wait after T1 reaches S2 dot signal. In this case, thread 1 execute wait here and print out 1, and then signal S2. So before thread 1 signals S2, the initial value of S2 was 0. After this signal, the counter value of S2 becomes 1. And then because we assume that T2 reaches its wait after T1's signal, so T2's wait simply reduce the counter value by 1, making it 0. So T2 can still go. So T2 prints out 2. And if at the same time T1 reaches the wait, loops back. And then after printing 2, T2 signal S1. So as you can see, the output value is 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Hope these two execution sequences can help you understand the details. Now, in the next few slides, it's just some simple discussions. Now, what if the initial value are changed to S1 being 0 and S2 being 1? Pause and figure out what answer it could be. Of course, the output will be 2, 1, 2, 1, 2, 1, 2, 1, because these two are quite symmetric. If S1 is 0, S2 is 1. So as thread 1 is blocked, thread 2 goes ahead. So thread 2 prints 2 first and then allows thread 1 to go. So thread 1 prints 1. So the remaining would be exactly the same. So this one is easy. Now, what if both initial value are changed to 0? This has to be 0. So what if S1 and S2 are both 0? Pause, please. Deadlock. What does that mean? Remember, this is 0. So if both initial values are 0, thread 1 execute S1 dot wait is blocked. And thread 2, because S2 initial value is 0, so thread 2 is also blocked. Thread 1 waits for thread 2 to signal it. Thread 2 also waits for thread 1 to signal it. So both threads are blocked by their wait calls, waiting for the other thread to call signal. So each of the two threads are blocked by an event that can only be caused to happen by the other waiting thread. Therefore, we have a deadlock. The system simply stop their execution, because each of the two threads is waiting for the other to act, but the other won't be able to act because the other would wait for me to do something. Now, finally, what if the initial value of S1 and S2 are both 1s? This one is a bit complex. I hope you could stop here and find a piece of paper and pencil to figure out the answer. I'm sure everyone would get the answer right. But to get the answer completely right would require some thinking. So please pause. because the initial value of S1 and S2 are both ones. So S1 and S2 are different semaphores. So thread 1, thread 2 could call S1 dot wait and S2 dot wait at the same time without the atomic execution requirement. Atomic execution is only applied to the call to the same semaphore wait or signal. So we really don't know which thread can get here first and get through S dot wait. It could be thread 1, could be S2. Even though thread 1 could get through S1 dot wait first, thread 1 could be switched out. And then thread 2 get through and print 2. So in this way, which thread can pass through its wait is unpredictable. And even worse, after they could get through the S1 dot wait first, this lucky thread could be blocked due to a context switch. And the unlucky thread gets through its wait and print out its value. So the output from thread 1 and thread 2 is kind of random. I hope you understand this. So it is very easy to get 2 consecutive 1s and 2s. Why? If thread 1 calls S2 signal before thread 2 can reach S2 dot wait. In other words, thread 1 finishes printing 1. And the thread 2 may still be here doing something. Then thread 1 calls S2 dot signal, increase the value of S2's counted by 1, which originally is 1. So now S2 dot wait, when it checks the value, is 2. So recall the countdown lock. We could allow 2 calls to S2 signal to pass through without blocking. So if thread 2 is lucky, it could simply print 2, come back, because after signaling thread 1 and thread 2 comes back to print 2. So you'll see we are able to print 2 next each other. Now, because the code between thread 1 and thread 2 are symmetric, of course, it's very likely that you could print 2 consecutive 1 together. So here is an execution sequence. Illustrates we have 1, 2, 2, 1. Now, this is the last slide for this lecture. I ask you to do a few simple exercises. Is it possible that thread 1 and thread 2 could print 3 consecutive 1s or 3 consecutive 2s, such as 1, 2, 2, 2, 1, or 2, 1, 1, 1, 2, or even worse? Can it be possible that you printed the previous example could print out 1, 2, 2, 2, 2, 4 2s followed by a 1? Think about it. It's not difficult. Now, let's extend this example a little bit. Suppose thread I can only print the value of I. Modify the simple code by adding semaphores and thread to do the following. The first one is print 1, 2, 2, 1, 2, 2, 1, 2, 2, 1, and so on. So between 2 1s, there are always 2 2s. And modify the code again so that it will print it out 1, 2, 3, 1, 2, 3, 1, 2, 3. The third exercise would be modify probably from this program, so that your program will print a 1, 2, 3, 2, 1, 2, 3, 2, 1. That's going up, going down, going up, and going down. And finally, the fourth exercise will be modify this program so that its output will be 1, 2, 3, 2, 3, 1, 2, 3, 2, 3, 1, 2, 3, 2, 3. These are very simple examples because you have the code templates, some easy modification with careful thinking. You should be able to do that. So in the next lecture, we're going to talk about a very well-known and very influential example and its various solution. It's referred to as the dining philosopher's problem. So let me stop here. See you next time. Goodbye.